Alrighty, welcome to lesson 1.2 on parent functions. So this is the lesson we did in class. Now, what we did in class, or what we're going to do in class, depending on when you're watching this, is kind of a jigsaw activity. It's going to be each group is going to explore a given parent function, and then students are going to share the features of these functions as a class, and then we'll all kind of copy down notes. But if you missed class, or if you just need to go over it again, or maybe we got cut short on time, I don't know, here's the video, okay? And I'm basically doing the part of every student, yeah, okay. So lesson 1.2 notes, we got on parent functions. Oops, there's it. Parent functions. So what is a parent function? And you could just read this word for word, but I'll say it out loud. Parent functions are the simplest form of a given family of functions. A family of functions is a group of functions that share the same shape for their graphs. So example, you can view the family of parabolas below. We'd ask, which is the simplest of these graphs? And what do we even mean by that, right? So you can see all of these parabolas here, right? This guy, and then this guy, and this guy, and this guy. And if you notice, they're kind of moved around, or they're stretched, or they're flipped, right? And they're all pointing to this mystery function. There is a very basic parabola that might look something like this. It's not the best little highlight drawing, but whatever here, right? It's the simplest parabola created by the simplest equation. We're actually going to see that a little bit later. But all of these, right, it's like a family. They're all the offspring of the parent parabola, which is just the simplest one. The equations of all of these graphs are more complicated than the parent. And you're going to see why there's why there's a simple one, okay? But before we get started on graphing those, some important vocabulary review. Hopefully we know most of these words. Some of them might be new, but this is just kind of, you got to know these words, okay? Because if we don't know the words, we can't explore the features of the graph, right? Now I'll do this in blue, and I'm only going to quickly go over this. So, domain, we've talked about this, is the set of inputs for a function mapping, right? Remember, I do like a set like this, call it A, a set like this, call it B, and then I map elements from A to B, right? A is the domain, B is the range. And so that's, set of inputs is the domain, set of outputs is the range. We've talked about that. An intercept, a very familiar word. This is where a graph of a function meets either the x-axis, which is given by the line y equals 0, or the y-axis, which is given by the line x equals 0, okay? Now, technically, intercept just means touch. So, we could ask, if I had two graphs right here, whoo, there's one graph, and then whoo, there's another graph. Where do they intersect, right? Where's the intercept? Well, it'll be like right there, right? It's where they meet. But usually talk about intercepts in the vein of where do they cross the x and y axis. So if I were to draw a little Cartesian plane here, I'll just make up a function. I'll go, woo, like this, right? I have a few intercepts. I have, you know what? I'm gonna adjust this just a tad because the y-intercept is at the origin. Here we go. Okay, I like that. That one's a little bit better. So, right, this, and this those 3 points are where the graph meets the x-axis. Those are x-intercepts. And that point right there is a y-intercept. Yeah? Okay. Say that's y, that's x, and another x. Okay? Asymptote, what's that? And so what I've given in red here is the official definition of an asymptote. An asymptote is a line such that the distance between the graph and that line approaches 0. Specifically, the distance between that line and that graph. Sometimes you may have interpreted this in Algebra 1 as, oh, it just gets close to that line. Well, yeah, kind of, but we're going to see in Algebra 2 that you can actually go over the line sometimes. You can even go back and forth over and up around the line. But for now, here's the basic idea. Here's an asymptote, and I'm going to make a graph that looks kind of like that. You know what? Let's make it even better. I want to really get an idea that it's close to it. Yeah. I want to align that's close to the graph, and then kind of comes out like this. So you can see that the distance between that is getting smaller and smaller, right? Where the idea is, oh, it's a long distance, and then it's shorter and shorter and shorter, and hopefully it's getting short, like that. Okay? Okay, axis of symmetry. This is just a line that marks the symmetry of a graph, or it's kind of where a graph looks mirrored. So we're going to see, let's see something like this. Like, I guess I could just be really basic and do a parabola. Sure, why not? I'll do a parabola because it's basic and easy, right? There it is. There's a parabola. You know what? I don't even want that. I'm just going to do that. If I draw this axis right here, you see how that's symmetrical on both sides, right? The right side, if you mirror it over this axis, you get the left side, okay? A minimum is just as small as y value. So I'll draw a graph like this, and I'll go, well, you know, it's best exemplified with parabolas, honestly. If I draw a parabola like this, I say that's a minimum. Whee! And then a maximum would just be the greatest y value. So I'm going to draw like this, get a nice straight line, and then I'll have maybe a parabola like upside down, like so. It's not perfect, but it's okay. And then this apex point, right, this top point, the highest point on the graph, that's the maximum, okay? So that's my min, and that's my max. Pretty basic. The vertex is the turning point of a parabola or absolute value function. So you could have a parabola like so. That's called the vertex. It's that turning point. You also might have an absolute value function, which looks like this. It's kind of a V shape, and that's a vertex. Okay, so both of those are the vertices of those graphs. Yes. Okay, next is inflection point. Now this is maybe something that might look a little bit different, right? So what is an inflection point? I don't even need the graph. So I'm going to draw a curve that looks like this. No, not that actually. No. Come on, Mr. Spake. There. No. Nah. Okay, I like that one all right. I mean, it doesn't have to be perfect, but I just wanted something to really get at the idea here. So what's an inflection point? A point where a graph changes concavity, which we could call the curvature. So the inflection point of this sketch I've drawn is about right here. Something like that. I'm kind of estimating here. But an inflection point is where the concavity changes, and the concavity of a graph, I like to say that it's kind of like where the graph is scooped, all right? Look to the left of this point. Yeah, look to the left over here. Which direction is it scooped? Is it scooped downwards or upwards, right? I'd say, oh, it's like it's scooped this way, right? The scooping is right this way. And then, if I look to the right of that point, the scooping is changed. And now it's kind of scooped upwards, yeah? And this is what's meant by concavity. The curvature of the graph has changed from this sort of scooped downward shape to the scooped upwards shape, okay? But the graph is still increasing. It's still going up. I guess there's a small interval when it goes down, but whatever. That's what's meant by inflection point. This will be covered more in calculus, maybe a little bit in pre-cal, because that's when we really care about inflection points, and we're going to talk about them. But that's not this class. So you're going to see the inflection point for a few parent functions, but we're not going to do a whole lot with it, okay? Lastly is end behavior, and that's just the behavior of f of x as x goes to infinity. Okay, so if I draw a graph like this, right? What would I like to say? Maybe I'll just say this. I'm going to make a curve that kind of goes like that. All right? Something like that. And you can see in this example, right, as x goes to the left, which is negative infinity, well, where does f of x go? I would say that f of x goes up to infinity. Do you see that? Right? As the graph goes to the left here, where is it going vertically? Well, it's going up. So I say as x goes to negative infinity, f of x goes to positive infinity. Vice versa, if you look on the right here, I would say that as I got a limited space now, as x goes to positive infinity, so as I go to the right here, f of x goes down, right? So it's going down and down and down to negative infinity. So I'd say then f of x goes to negative infinity. And this is an example of end behavior to kind of get it down. Okay? All right. So those are features of this graph. If you didn't know them, I should have stated at the beginning of the video that if you already knew this, you could have skipped this part. Oh well. If you didn't, whatever. Okay, let's go. I don't want to take too long on this. Me and my fiance would like to go to Raising Cane's. This would be lovely. I would love to get Raising Cane's today. The Caniac combo. But I can't decide right now. Should I get a Dr. Pepper or a sweet tea? Because you see, Raising Cane's has great soda, but it also has fantastic sweet tea. Okay, well, this is a decision I'll have to make in the future. Anyway, graphing parent functions. Here we go. We're going to start with linear. We know how that goes, right? Good old-fashioned linear. Now, these are the simplest functions, okay? A parent function is the simplest equation. It's creating that graph. So y equals x creates a straight line, which we're going to see in a second. Here's my suggestion. Well, to graph these parent functions, here's kind of the routine that I'm giving to everybody in class. You need to have, anytime we're graphing in here, you need at least 3 points, okay? And when I say 3 points, we really would prefer something that's visible. Okay, so like, look, 5, 4 is right there. But if I said like 1/3, 2, okay, well, that's like here. I don't know, right? It's hard to see the 1/3 on this grid. So try to go for whole value points. Not all functions are going to be perfect, and I know that. And you're going to see as I go through some of them, that's not going to happen. But the idea is we want to try 3 accurate, nice, neat points. And if we have to kind of estimate it on the graph, that's fine. But we definitely want to write the points down in a table so our reader, our audience knows what we're talking about. Okay? Now, when you deal with parent functions, we're exploring things. We're trying to figure out what the graph of these things look like by hand. We're not really using a calculator here. There will be one function you're going to use a calculator for. But to figure out the shape of this, you just need to generate a list of points. And then you need to graph those points to observe the behavior of where the graph's going. My suggestion is, for almost every one of these single graphs, start with -2, -1, 0, 1, 2. Here's the reason. These are the simplest graphs. So those simple numbers, 0, 1, 2, are pretty good. And this is a wide enough interval. They're all centered around the origin at 0 because they're the simplest. And so we get a little bit to the right, a little bit to the left, and that's kind of the idea, okay? But you'll see as I go, it's not always going to be those 5 points, but those are a good starting point to try. Okay, so with linear, you should already know this. If y equals x, then if x equals -2, y equals -2, right? So, okay, that's -2. Oh, and if x is -1, then y is -1. If x is 0, y is 0. If x is 1, y is 1, and 2, and so forth, right? And if we want, keep going. You could say 3 and 3, 4 and 4. It doesn't really matter, okay? And I'll plot all these points. say negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Of course, I don't want to do this all day, right? But I can see that the linear makes a straight line. So I'm going to take my pen and draw a straight line from corner to corner, like so. That is the linear parent function, yeah? And since we've spent our first day of class talking about domain and range, you should be able to figure out the domain and range of each of these graphs just by graphing them, yeah? If I look at this graph, I will find, and I'm going to give this an interval notation, the domain of this graph is all real numbers. It spans from negative infinity to positive infinity. You can see that because it's defined for all real numbers left and right. Similarly, it's defined for all real numbers up and down. It's a straight line, right? So the range is also all real numbers from negative infinity to positive infinity. You'll see that the x and y intercept are both shared at the origin, 0, 0, and 0, 0. Yeah? So that piece is shared. And done. These are the features of the linear parent function. And that one I did in class. But the others are up to you guys. Now I'm walking through this because maybe you missed class, okay? So we go to absolute value. Well, I hope you've seen the absolute value sign before. If not, that's okay. Here's a quick definition. Absolute value is defined as the distance from 0, okay? So I'm going to take the same inputs, negative 2, negative 1, 0, 1, 2, yes? And ask yourself, right, if I have absolute value of 0, how far away is 0 from 0? It's not. It's not far at all. It's 0. There's nothing. No distance is passed. What's the absolute value of 1? Well, 1 is 1 away from 0. What's the absolute value of 2? Well, that's 2 away from 0, right? So I'm getting these points, 0, 0, 1, 1, 2, 2, and I could keep going. But how about the absolute value of negative 1? So you ask yourself, how far away is negative 1 from 0? Well, it's 1 away, right? If you think of distance, the idea of distance is we don't have negative distance, right? So it's negative 1, 1. And then the absolute value of negative 2 is 2 units away, so it's positive 2. And so I get this. And so this is creating that V shape, right? And so if you want, you can do negative 3 is 3 and 3 is 3, right? So I get these 2 points. And you see that it's going to just keep doing that. So I have a V shape. I'm going to draw kind of like, it's not bad. Here we go. Let's try that again. Boop. There we go. Nice straight line. And I'm going to draw this one. Say right here. Straight line. It's not perfect, but it's good. Okay? And this is the absolute value graph. Okay. So what is the domain and range? Well, if you see the domain, we have a graph defined for all real numbers left and right. Yeah? So domain is negative infinity to positive infinity. It's all real numbers. However, what about the range? So if you're reading it vertically, right, we start down here. Do I see a graph down here? No. So I'm going to travel up and up and up and up and up and up and up. And then the graph starts right there. And that point is 0, right? So you see the graph is starting at 0 and it's going up to infinity. So my features are 0 to infinity. Does it include 0? Yes. So it is a bracket, okay? Bracket 0 to infinity. And then you'll see that it also has an axis of symmetry. If you notice, I'm going to draw it with a little blue dashed line here. If I draw this little blue dashed line, you'll see that this cuts the graph in half. And if you were to mirror the right leg over this blue line, that would be the same, right? It'd be the same image. So the axis of symmetry is the y-axis, which is the line x equals 0. And I'd like to point out to you, it is important that you establish what variable. When you deal with lines, you either got to say x equals 0 or you got to say y equals 0 or some number, right? Because x equals 0 is a vertical line, but y equals 0 is a horizontal line. And we need to remember that, okay? You'll notice that the vertex is a minimum. I want to go back to red. The vertex is a minimum at the origin, 0, 0. Because it's the smallest point right there. It's the lowest point on the graph. Okay? All right. Let's move on. Quadratic. Now, he should be familiar. We test our -2, -1, 0, 1, 2. And keep in mind, we're just plugging numbers into the function. So we say y equals x squared. Well, 0 squared is 0, because it's 0 times itself. 0. 1 squared is 1 times 1, that's 1. 2 squared is 2 times 2, that's 4. I could do 3. I could say 3, right? 3 squared is 3 times 3, that's 9. But, I don't want to just do positive. I want to analyze what it looks like on the left as well, right? So we try -1. I say, okay, well, -1 squared is -1 times itself. 1 times 1 is 1, but negative times negative is positive. So that's +1. So that's +1. If I do -2 squared, that's -2 times -2, that's now +4. And so I get a +4 here. And, if you were to do -3, I would also get +9. You can verify this by plugging it in. So I get 0, 0, 1, 1, 2, 4, 3, 9. So it looks kind of like that. -1, 1, 2, 4, 3, -9. And you see that this is kind of a U shape here, right? So I'm going to kind of lightly, I'm going to try and get a nice parabola here. By the way, that's what this shape is called, if you don't remember. This U shape of a quadratic function, x squared, is called a parabola. Like so. Okay? Remember, I just take my time on this. I take my time in these videos. If I'm going too slow for you, just speed it up, skip along, increase the playback speed, whatever. Okay? I like to take my time. I'm just chilling on a Sunday. That's the date, by the way, if you see it up there. Oh, I tried to tap, but will the laser pointer go? Nope. Oh, no, it doesn't. Okay. Oh, you know what? In case somebody talks to me, do not disturb. I should always put that on. Okay. Domain. You'll see that the domain, just like the previous graph, is all real numbers. -infinity to +infinity. It is defined for all real numbers left and right. Again, just like absolute value, there's nothing down here, right? No graph in the negative y value region. It starts at 0, and then it goes up to infinity. So just like absolute value, the range is bracket 0 to infinity. The axis of symmetry, just like absolute value, it's symmetrical on both sides here. And so that is the line x equals 0. And also, just like absolute value, it's a vertex with a minimum at the origin, 0, 0. Ta-da! And that is the parabola. Okay. Shape called parabola. Okay? And you'll notice it's a V shape here. Okay? Okay, square root function. So we're going to graph now y equals square root x. And so I'll do the typical points, -2, -1, 0, 1, 2. And let's analyze this. So y equals square root x. I'll say my input is -2. What's the square root of -2? Well, we talked about this on the first day. I can't take the square root of a negative number. Well, actually, I can't. But I don't get a real number, okay? We're graphing on the real plane. And so square root of -2, not a real number, does not exist. You can't graph that. Can I graph the square root of -1? No, that also does not exist. Can I graph the square root of 0? Yes, because that's asking what times itself is 0. 0. So I do have a point at the origin here, 0, 0. You're going to find that almost all of these graphs has a point at the origin. There's maybe a couple exceptions, a couple or 3 exceptions to that. And then I'll do square root of 1. We know the square root of 1 is 1, so that's 1 comma 1. Ooh, but what's the square root of 2? The square root of 2 is, if you could guess, the square root of 2. But do you know what the square root of 2 is? And if I restrict you to not using a calculator, do you know? Do you know that it's approximately 1.414? Have you memorized that or not? I don't expect you to have memorized the approximation for this. So let's not do 2, yeah? Could I try 3? Well, I did the square root of 3. It's not a pretty number, right? It's like 1.7. So let's try square root 4. I say, oh, okay, well, the square root of 4 is 2. So, yeah. So look, I'm going to put a thing here. I'm going to say not pretty. Sorry to be judgmental and shallow, but you are not pretty. But 4 comma 2 is pretty. In fact, he's gorgeous. 4 comma 2 right there. I might ask you to pause the video and find one more, okay? Another pretty point, right? I call pretty points because they're just integer values. You try the square root of 5, square root of 6, square root of 7, no. Square root of 8, no. Square root of 9, square root of 9 is 3. So I do 9 comma 3, and I get that point. And so now I can kind of connect these, right? I have an idea of what the graph looks like here. Ta-da. Like so. There's kind of ugly arrow. Yeah, that's a square root curve. You might notice, doesn't that look kind of like the parabola? I mean, if I were to take this and flip it upside down, wouldn't that look like a parabola? Food for thought. I'm not going to continue that, though. Okay? Domain and range. So if you look at the domain, actually, there's nothing out here now, right? On the x-axis, I don't have a graph out to the left anymore. It starts at 0 and goes on and on forever. So the domain is bracket 0 to infinity. The range, similar, starts at 0, goes up to infinity. So it is bracket 0 to infinity. It does have a minimum, and we don't call that a vertex because it's not a turning point, okay? The graph doesn't change or something, it's not a vertex, but it is a minimum because it's the lowest point on the graph. It's at 0, 0. And now we'll talk about this end behavior business just to kind of get used to talking about that. As x goes to infinity, so as I go to the right, what's going on? Well, as x goes this way, y goes up. So f of x goes to positive infinity. The next piece, though, it says as x goes to negative infinity. Well, we might actually, and I shouldn't have typed this actually, because this is wrong to say. What happens as x goes to negative infinity? Nothing. There's nothing to do over here. Where's the end? It's at 0. So actually, what we should do is we should cross this out. And we should say as x approaches 0, because that's the left side. Yeah? Then f of x approaches what? Well, as I go to the left, right, I'm approaching this way, all the way to 0. Where's the y value going? It's also going to 0. So I'd say f of x goes to 0. Okay? All right. And that's that. So I guess my definition over here, I should have changed it. The end behavior is how it behaves specifically on the ends. Now, if the ends don't go to infinity, if they stop at a particular point, then that's where we're going to be talking about. Okay? All right. We are about halfway there. Let me try to kick it into gear here because we would like to leave for Raising Cane's within the next 30 minutes before 1 o'clock, and that would be nice. Okay, the next up is the cubic function. Now we're really getting into Algebra 2 functions. It's possible you saw the square root function, but I don't know if y'all have seen cubic and cube root, things like that. So let's look at it. Again, we'll do -2, -1, 0, 1, 2 as a basis, right? What is 0 cubed? Well, 0 times 0 times 0 is 0. What is 1 cubed? That's 1 times 1 times 1 is 1. What is 2 cubed? That's 2 times 2 is 4 times 2 is 8, right? We could ask ourselves, what's 3 cubed? Well, 3 cubed is 3 times 3, which is 9, times 3 is 27. Am I going to graph that on this? No. I don't have a 27. It's unreasonable to graph that here. Okay? Okay, look, I've got 0, 0. I've got 1, 1, and I've got 2, 8. Whew, kind of big right there. Kind of a big jump, right? What about -1 cubed? Is this going to look like a parabola? -1 cubed. That's -1 times itself again. Well, 1 times 1 times 1, the magnitude of that is 1. But a negative times a negative is a positive times another negative is negative. So -1, -1. It's down here. Now how about -2, right? -2 times -2 times -2. Well, 2 times 2 times 2, that's that 8. But 2 negatives makes a positive. 3 makes another negative, so it's -8. -2, comma, -8. So I'm going to go over 1, 2, and down -8 like this. And this is the cubic parent function. I'm going to try and draw as best I can. It's a lot easier for me to do this on paper and pencil than it is on an iPad with an Apple Pencil. I'm not very good at using the Apple Pencil. Now, you want to try and get this curvature nice and defined here. It bends in this middle region, okay? Kind of bends like this. And then it goes up. And I know that looks kind of straight, but it's just that it's growing really, really fast right there. Okay, more or less it looks like that. I might fix it a little bit later, but it looks something like that, okay? What I want you to draw your attention to is this is an example of that concavity changing. You see, to the left of this point, it's scooped downwards, but then after this point, it's scooped upwards. So that is actually an inflection point, which is why we said that earlier, okay? The inflection point's at the origin, so it's 0, 0. The domain, if you recognize, is, oh, look at that, it's all real numbers. And the range, oh, it's all real numbers. So it's -infinity to +infinity for both. Okay. And now end behavior. As x goes to +infinity, as I go to the right, the function goes up. So that's +infinity. As it goes to the left, the function goes down forever. That's -infinity. So looks like that. Okay? Because this is the left and right ends. Okay, let's try the next one. So that's the cubic function. Get familiar with that graph. And the next one's cube root. And so I say, what's the cube root of x? Well, I'll do -2, -1, 0, 1, 2. Cube root is 0. Now, so if a square root is what times what is that thing, right? Square root of 4 is 2 because 2 times 2 equals 4. So the question is, what times what times what, all being the same number, equals 0? Well, 0, right? But how about 1? What times what equals 1? Oh, well, 1 times 1 times 1, 1. How about 2? Well, it's the cube root of 2. And I don't know what the cube root of 2 is. Yeah? So I go to cube root of 3. I go to cube root of 4, 5, 6, 7, 8. Hold on a second. Think about it. If you're doing these triplets, right? 0 times 0 times 0, and then 1 times 1 times 1. What's the next one you're going to test? Well, 2 times 2 times 2, which is 8. So I'm going to use 8, and the cube root of that is 2. And don't you notice that that's just the flip of this, right? It's just reversed. I'm just reversing everything. So 8 goes with 2. And you might see that 27 goes with 3. Okay, cube root of 27 is 3. Now, how about the cube root of -1? Now, is this like the square root where I don't get a real number? So we ask ourselves, is there something times itself again that gets me -1? Well, I know that 1 times 1 times 1 gets me 1, but that's not positive, or that's not negative. What if I make it -1? Does -1 times -1 times -1 equal -1? Oh, hey, hold on. It does. So it's -1. Yeah? It's -1. And incidentally, the cube root of -2 is negative cube root 2. Aha. So actually, I might write out here, but I don't want to graph that one. I'm going to graph the cube root of -8 is -2. And that's what's going to work. Okay? That was a little, this one I know, this one's a little more tricky. 0, 0, 1, 1, 8, 2, -1, 1, and then -8, -2. And it looks like that. Doesn't this look really similar to the cubic function, just a little bit different? Well, there's a reason for that. So, draw my little line. Make sure you get this nice curvature. It's that idea of the inflection point, just like our cube graph. The cube root looks similar. Okay? It looks something like that. You know, I really like the top leg. I'm not the biggest fan of the bottom. Let's try that again. I like this. You want to skip this part? You can. Looks something like that. It's kind of curved down. Sorry, I just want this to look pretty. Is it okay? Are y'all judging me? You saying, Mr. Spake, please stop wasting my time. I say, I'm sorry. Okay, there we go. It's not the best, but whatever. It's whatever. It's what I can manage on this silly iPad, okay? Okay, what's the domain and range? Well, domain is all real numbers. And so is the range. I know that it looks flat here at 2, but it's going to keep growing, okay? It's really slow, but it will keep growing up, okay? It's just, it's kind of like how this one almost looks vertical, but it's just because it's growing really, really fast. This one almost looks horizontal, but it's just because it's growing really, really slow, okay? The inflection point here is 0, 0. And my end behavior, well, as x goes to positive infinity, f of x does indeed approach positive infinity. It does go up. It's really slow, but it does it. As x goes to the left, it does go to negative. It does go down, okay? It's just, again, really slow, okay? Exponential. Now, this is the one, exponential and logarithmic are ones where I'm going to let groups use a calculator. And that's because I don't expect every student to know all exponent rules because, I don't know, depending on your Algebra 1 teacher, some of them go really in-depth in exponentials. Others, it's like one test and then you never talk about it again. So it's okay if you don't know all the rules, okay? I hope you know some of the rules, but it's okay if you don't know all the rules. We're going to have our own dedicated unit for exponentials later in the year. So we are going to do -2, -1, 0, 1, 2. And I know that you guys can do 0, 1, 2 because 2 to the power of 0, well, anything to the power of 0 is 1, and that's a rule to know. So 0, 1 is actually right here. And then 2 to the power of 1 is 2. And then 2 squared is 2 times 2 is 4. So that's 4. So it's 1, 2, and then 2, 4. And if I do 3, then I do 3 squared. Oh, I'm sorry. Am I doing this wrong? No, I've been doing it right. I just messed that part up. It's 2 cubed. I'm sorry. 2 to the power of 3, right? You see it's 2 to the x. So it's 2 to the power of 3. That's 2 times 2 times 2. That is 8. So that's 8. And look, you can do 4, right? 4 is going to be 16. It's going to keep on going. But I can't graph 16. So 3 is going to give me 8. That's 9. I want 8. Like so. Okay? But now what's going on the left side? What's 2 to the -1? I'm not going to bother telling you the exact rule today, okay? 2 to the -1 is 1/2. And that's what people with calculators are going to find. So -1, comma, 1/2. And like I said, we want to avoid those, but at some point, you're going to have to. At -2, 2 to the -2 is actually 1/4. So it's going to get really low here. And then if you take a calculator, so this is 1/4. If you do 2 to the -3, you're going to get 1/8. And it's going to be even smaller. It's going to be tiny, tiny, right? And it's getting really close to 0. But you see a defining feature of an exponential function is that it has an asymptote on the x-axis. Because if you keep, here's maybe the logical intuition, okay? Let me erase these. If you don't understand how negative exponents work, that's okay. Because just look at what's happening to the y values. Times 2, times 2, times 2, times 2. So wouldn't it make sense if we just wanted to go backwards, divide by 2, divide by 2, divide by 2, divide by 2. What's 1 divided by 2? Oh, 1/2. What's 1/2 cut in half? It's 1/4. What's 1/4 divided by 2? It's 1/8, right? So that's why that's working. And if you take a piece of the pie and you cut it in half, and then you cut it in half, and then you cut it in half, and then you cut it in half, and you cut it in half, you're always going to have some little sliver of pie left over. You're never going to have 0 pi, right? I'm talking about a physical pi, not the number pi. So there's an asymptote at 0. Just kind of looks like this. So an exponential graph is really flat to the left, but not exactly flat. Just looks flat because it grows so slow. Okay. And that's my exponential graph. Okay? And we can look at this graph. We say, oh, the domain is all real numbers. We know that from Algebra 1 because it's defined left and right. But the range, the range. There's nothing down here, and it starts at 0. But it doesn't include 0 because it's an asymptote we're not touching. So the range is from 0 to infinity, yes, but it's not bracket 0. It's parenthesis 0 because 0 is at an asymptote. And that asymptote is y equals 0. Notice, this is where end behavior really starts being important. As you go to the right, right? As I move to the right, I'm moving to the right, I'm moving to the right, the function is going up, and that is infinity. But what about as I go to the left? as I go to the left, well, it's not going down forever. It's approaching an asymptote, and that asymptote is 0. So as x goes to negative infinity, f of x actually goes to 0. Okay? F of x goes to 0. I'm just fixing my... Oh, it's a terrible infinity. I just want it to look pretty. Okay. Done. And that is the exponential graph. The next one is logarithmic. Now, I am letting the group use a calculator to calculate logs because calculating logarithms is totally new. You've never seen it before, and we don't talk about it until like February, I think. Maybe February, okay? We're going to talk about it in February. We're not talking about it today. So, use a calculator, typing in these things, and you'll find that -2 does not exist. At -1, the function does not exist. At 0, it does not exist. At 1, it's 0. At 2, it's 1. At 4, it's 2. In fact, at 8, it's 3. And there's actually some more points you can do. And so, let me see, how could I add these? More points. More points. If you test fractions, which you wouldn't typically think to test, I'm going to draw a bar like this. If you test 1/2, you get -1. So at 1/2, it's -1. And if you test 1/4, it's -2. And it's going to look like that. And if you test 1/8, it's going to be -3. It's going to look kind of like that. Logarithms are actually very similar to exponentials, which if you notice these tables, don't they look kind of the same but flipped, right? There's a reason for that, and we will talk about it when we get to logarithms and exponentials. But for now, you're just kind of learning the shape of the log parent function to get an idea. It has a vertical asymptote on the y-axis. So it kind of looks like this. Okay, let's continue up. Looks like that. Ooh, that's a really good graph. I'm proud of that one. And if I gave you this graph, you should be able to figure out the domain and range. There's an asymptote at 0, which is x equals 0. So the domain is starting here around 0, but not touching it, going to infinity. So that is parentheses 0 to infinity. And notice the range up and down forever is all real numbers. Oops. There we go. And the end behavior, as x goes to negative infinity, f of x goes down forever to negative infinity. Oh, except this is another one of those times where it's kind of wrong. Okay, so this one I'm going to scratch out. Sorry. As x goes to positive infinity, as it goes to the right, it goes up forever. It's a little slow, but it does go up forever. But where is it going on the left? It's not going to negative infinity. There's nothing out here. It's going to 0, right? It's approaching 0 right here. So as x approaches 0, f of x goes down and down and down forever towards negative infinity, like so. Okay? When it comes to a logarithmic graph, right now, I only want you to be able to read it, okay? I'm not going to ask you to graph logs yet. We are going to have that as a specific unit dedicated. All this is a kind of, you kind of see what it looks like, okay? That's it. You're just seeing what it looks like, and you know how to read the graph. Done. Okay, there's one more, and then I need to go to Raising Cane's. Rational. And the rational function is 1 over x. And this is one of the trickiest functions that we're going to talk about all year. I saved it for last year. So we'll try, it's actually not too bad to graph. -1, or -2, -1, 0, 1, 2. Now observe those, okay? 1 over -2 is just -1/2. So, correct, because that's what we're doing, right? We're plugging in -2 here. So this is -1/2. So -2, comma, -1/2. Like that. -1 that's 1 divided by -1, which is just -1. So that's -1. So -1, comma, -1. Like so. 0. 1 divided by 0 is undefined. So actually, we write undefined. Does not actually exist there. Okay? And then you do 1 divided by 1 is 1. So I get 1. So I get 1 divided by 1 is 1. 1 comma 1. And then I get 1 divided by 2. 1 divided by 2 is, well, 1/2. So at 2, it's 1/2. But this is not nearly enough information. It just isn't. Okay? So I need to do more. I need to figure out some more points. I have no idea what this looks like, right? Is it this? What? What is it, right? So we're going to test some more numbers and some fractions. If I test 3, I get 1/3. So, okay, I get 1/3. If I test 4, I'm going to get 1/4. And you can see, okay, hold on. I think it's going to approach 0 this way. Yeah? That leg, if you just think about it, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 10, right? It's getting really, really close to 0. But kind of like the exponential one, it's not going to touch. So we're actually going to have an asymptote here at 0. I'll be helping the group along with this one. But let's test some more points because I don't know what's going on in the middle here or on the left side. So I need a number less than 1. How about I try 1/2? Well, then 1 divided by 1/2. Do you remember how to divide fractions? That's 1 times 2 over 1 is 2. It's 2. So at 1/2, it's 2. If I cut it a little bit more, I say 1/3. That's 1 over 1/3. That's 1 times 3 over 1 is 3. So that's 3. And so this is 3. And then you can guess 4 and 5 and so on. And so, if I do 1 over 10,000, is that, okay, first of all, if I do 1 over 10,000 as the input, that's almost 0. And if I do 1 over that, that's 10,000. So what that means is it's going to be really close to 0, but it's going to be way up here. It's at 10,000. So that means there's also an asymptote here. Whoa. So a rational function has 2 asymptotes, and then it kind of approaches this way. And that's my graph, like so. Oops. Okay. Now, you can replicate this on the left side as well using negative fractions, okay? If I do -1/2, I'm going to get -2. If I do negative 1/3, I'm going to get negative 3. And so what's going to happen is you're going to get this going on. Okay? And so it's kind of, it looks similar in this quadrant down here. It's going to go through this points and then down like this. And that's the rational function. This one's going to be the trickiest one. Okay? Now I want you to look at this graph. Whoa, what's going on here? Well, the function is defined. If you see this arrow, there's a function here on the x-axis. Think the x-axis as a number line. There is a function for all these values, and even here. But what's it not touching? 0. But then it skips, right? And then it starts again on this side, and it continues from the other side of 0 and goes on to infinity. You see, this is 2 disjoint intervals. It's the interval negative infinity up to 0, not including 0, and then it's the interval 0 to infinity, not including 0. How do you join those two intervals? The union symbol, yeah, which we talked about last class. So you need that union symbol to connect those intervals. The range is actually the exact same story. If you look at the range all the way down here, there's negative infinity up to 0 and then up to infinity. So the domain and range are actually both the same. It's from negative infinity to 0, union 0 to infinity. Okay? And that's it. So for asymptotes, we actually have 2. We have a horizontal asymptote, horizontal at y equals 0, and you have a vertical asymptote at x equals 0. There's 2. And if you notice the end behavior, as I go all the way to the right towards infinity, the graph goes down approaching 0. If I go all the way left to infinity, it goes, well, sort of upwards, but also approaching 0. So the end behavior is actually the same on both graphs. F of x is going to 0. Okay. Now, before I end the video, because I'm about to, because it's Raising Cane's time, baby. Before I end the video, rational and logarithmic are not a major focus, okay? Let me put that in yellow. Rational and logarithmic are not main focus on test. Okay? I just want to say that. The rational, so this one we just did, number 9 and number 8. I would like you to kind of be familiar with the shape, most particularly how to read the domain and range. So you might see the graph of a rational function, but all I'm going to ask you is the domain and range. I'm not going to ask you to like graph it by hand or whatever. Recognize the shape, the name, and its domain and range. If you can do that, it's good enough for now. Okay? Same goes for logarithmic. If you don't know how to make this table by hand, it's okay. Just recognize that this is what the graph of log looks like. And if you know what the graph looks like, you should be able to figure out the domain and range. Okay. Well, that is all the parent functions. And that is just a walkthrough through all of them, which again, I didn't talk in class like this, just me. All of you, the students, the lovely exploring students, found this out for your own and then shared with each other. Okay? So, I will make a short part 2 of this video, just for this last part. It's Algebra 1 review on increasing and decreasing functions. That's not in here. Okay? So, if you would like to see the continuation of this video, go click on the next one. Thanks for listening. This one was a long one, but I hope it was helpful if there was anything in class that you just weren't quite getting yet. So, yeah, again, thanks for being here. Take care and have a good rest of your day.